Okay, so if we have this vector function, RT cosine Ti plus sine Tj plus Zk, I just threw this out to see, what kind of shape does that make? Everybody here? Small group, but everybody here told me it said spiral, but it gestured for a helix, okay? Called a helix. A spiral is just in one dimension, or in two dimensions. Now you can have a rising spiral, okay? But this is your helix. It's a circle in the XY plane because well, let's do it in order. Cosine squared t plus sine squared t equals 1. That's your circle. And constant increase in the z direction. Okay. Now if we modify it, where r equals, let's say, and it's I, J, and ZK, how's that going to differ? You can just gesture. And let's make that z squared, okay? So I tend to do abstract myself by not writing the i's and j's. Okay, well, in the xy plane, as now it's the t. Okay, and this should have been a t up here, not z. I want this to be a t squared. Okay? So root z there, because of course, well, you don't have to worry about it. You asked me how I was doing, that was a pretty good indication. Okay? But you understood what this was anyhow. Constant increase in the z direction because it's t. Okay. Okay, now here. Okay. What happens as t gets bigger? Well, it's like your circle keeps getting bigger, but then it's not really a circle. That's a spiral. Well, it's an Archimedean spiral, okay? Spiral that moves away from the origin or away from the center, if you wish, at a constant rate, okay? And then what happens here? Well, this is increasing faster and faster, kind of like a uniform acceleration upward. Since everybody here's in physics, so and we're exactly what we're talking about there. Okay, so you could sketch this. You could sketch this one pretty easily, but this one's a little more interesting. So down here in the XY plane, you start at the origin. And then as t increases, it's like the angular position down in the plane increases along with t, and t's like your angle here. Okay, so here's t, and then a little later, here's another t, and these aren't really t's because they aren't the same, but you get the idea. Your angle here keeps increasing, and your distance from the origin increases along with that angle. Okay, so you double the angle, you get this, you triple the angle, and you get out here, and it keeps spiraling outwards. It gets back here and out here, Yeah. So you see what's happening. Let's go ahead and let's move this all the way back to here. So, kind of comes around like this. And it's going to come around here and get further out. Okay? Now I'm just going to draw the part that's in the XY plane. So those are the points down in the plane, and the path followed here, the R vector, okay, follows a path above this spiral. And that path moves out to t squared units. Now, t would be pi over 2 here. So t squared would be pi over 2 quantity squared. Pi over 2 is about 1.6. You square that, you get about 2.5, 2.56. It's a little less, but it's about 2.5, and this is about 1.5. So you would have a point maybe up here. Okay? For t equals 0, of course, your point would be the origin. For t equals 1, which might occur along about here, then you'd be up maybe here. Okay? Now for t less than 1, you're squaring numbers less than 1, and they get small pretty fast. So you square this one, maybe it's only this. You square this one, maybe it's only just a little bit above this point. So now you've got this path here. And you can kind of shade this, to see, to make it clear that this path lies above this part of the spiral. I mean, of the spiral down in the XY plane. So you've got a path that's increasing like this, okay? And then it's going to keep going up here. It gets a little complicated because you get, well, we'll see that. Now, where we're going with this is, if you're following this path and t is time, and we often interpret our parameter as time, although there are other interpretations, as you're going to see, that are real important. This is a motion in time. So you're moving around this spiral, and your angle here is changing at a constant rate. Now, as the angle changes at a constant rate, your speed here keeps increasing. Your angular position changes at a constant rate, but your distance from the origin changes, okay? Also, at a constant rate in t, okay? So your velocity here, well, it turns out to be always tangent to the curve down in the plane. So you could have velocity vectors here, maybe, and these are constant. Up here, now if it was this equation, the t would, well, t is increasing at a constant rate, so that the k is increasing at a constant rate. So if it was this picture, your speed would be constant, okay, the length of your b vector. Down here, since you got this t squared here, well, that's going to increase faster and faster. So if you want to sketch velocity vectors corresponding to the actual, okay, so maybe you've got a vector here. It's about the same length as this one, just a little longer. A vector here, it's significantly longer than this one. And a vector here, that's all the way up into my equation. When the vectors get into your equation, you know they're getting big. Okay, get the idea? Well, I'm going to foreshadow the calculus of this thing, which is coming right up, so that I can say that the velocity vector, and given your understanding of physics at this point, it's no surprise that that velocity vector is a derivative of your position vector. Okay, it equals what? Well, by the product rule, it equals cosine t plus t sine ti, and then put these in a column. Okay, derivative of this is going to be sine t plus t cosine t, and then plus tk. Make sense? Now, if we did this one, just by contrast, you'd have b equals sine t I plus cosine tj plus k, right? Just take the derivative. Okay, no big deal. Okay, what's the speed? It's the magnitude of your velocity. And you can do that in one of two ways. You can use the Pythagorean theorem and just square this and square this and square this and add them up. Okay? Or you could just do v dot v and get the same thing. So I'm going to do v dot v because we want to think in terms of vector operations. But either would be okay. And now I'm going to risk doing the algebra in my head. So watch me. But you're going to get just squaring the binomial. You can use a special product or you can use a distributive law. Special product, you know, a plus b quantity squared is a squared plus 2ab plus b squared. You use that enough that you kind of want to think in terms of that special product. You know, special products you learned in algebra. Maybe haven't used them as much as you'd hope, but they're handy. And hopefully that was drilled into you pretty well in your algebra course. But anyhow, and then you get sine squared t plus 2t sine t cosine t plus, man, I just, okay, look here. The derivative of the sine is the negative of, the derivative of cosine is the negative of the sine, right? So I'm looking forward to what I'm going to get. And I'm going to have a negative, well, I'm going to have a sine here and a cosine, so that's all right because the sine has positive derivatives. Okay, so I've got a negative here. And I didn't realize till I got here because I know that these two terms are going to add up to 0 or cancel out. And I hate the word cancel because people don't cancel right. But at this level, I think I can trust you to cancel right. Okay? The level of pre-calculus, forget it. Somebody sees an X here and sees an X over there, and the next page I'll cross them out and make them disappear. It won't even make them one. Okay. So anyhow, you get this, and then plus t. Plus t squared, sorry. Okay? Now, that simplifies. These add up to 0, and you got 2 cosine squared t and two cosine squared t's and 2 sine squared t's. That just gives you 2. There's 2 times the quantity cosine squared t plus sine squared t. You get 2 plus t squared. Comes out very simple because of the Pythagorean identities. So there's your speed. And you see it's not constant. That's why these vectors, that's not why these vectors get longer, but that's a rigorous confirmation of the fact that these vectors get longer. You can do a rigorous geometric argument as well, but the derivative gives you a handy way of symbolizing. Speed is increasing. And if you were to unfold this, okay, take this little segment, of course you can extend it as far as you need to. Take this little segment here and unfold it. You would have your z coordinate and your t coordinate that goes out to pi over 2. And your function here would be 2 plus t squared, which has a graph that looks like this. Okay? Now if you were to do the same thing here, I screwed up. This isn't your speed, this is the square of your speed. Okay? So speed is the square root here. The square root of all this, okay? So I guess that square root sign goes over everything. It's the square root of 2 plus t squared, so I lied. My graph here should be the square root of 2 plus t squared. Which won't look exactly like this, because as t approaches infinity, 2 plus t squared approaches t. Simple analysis, okay? And common sense. If t is 1,000,000, t squared is 1,000,000,000, and 2 doesn't make much difference at all, right? So when t is really big, this is really close to t. So my graph was originally an upward parabola, but now it's going to approach the line z equals t as an asymptote. And you want to ponder that. If you don't understand that based on your knowledge of pre-calculus, then you didn't have enough hard problems in pre-calculus. And personally, I think I'm not being critical of your teachers, okay, because you're obviously well prepared, and you've obviously learned what you need in order to succeed in this course, which is excellent. But if I was teaching really bright high school kids, I would want to give them some really hard problems that I wouldn't expect B students or even low A students to get. So you think a little more deeply and come in able to do this stuff even better. Of course, if I was a high school teacher and did that, I'd get fired, because parents would object. My little Johnny can't do that. Well, okay, so your little Johnny is not in the upper top percentile. 99 people out of 100 aren't. Little Johnny's perfectly bright. You know, he's probably in the 80th percentile, but you can't expect that we're going to limit education to the lowest common denominator. Johnny's bright. Johnny's doing great. Johnny's going to make an A. Okay? But Johnny can't do the hardest problems. There are problems you can pose in pre-calculus the PhD would have trouble with. Probably not for long. Okay? But they can get really tricky. I'm digressing all over the place, but there's a problem where you've got a disk. It's a flying saucer, and it's got one engine on it over here, so it's firing this way. Now, it's gonna spin, but it's also gonna go forward. What's its motion? They gave this to a bunch of PhDs and less than half of them could solve it. It's simple. Okay? Fermat's last theorem. And hopefully you're familiar with that. If not, look it up. It took an act of pure genius to prove the stupid thing. It's x squared plus y squared, or x to the n plus y to the n equals z to the n. They're integer solutions only if n equals 2. Like 3 squared plus 4 squared equals 5 squared. And to prove that, you had to go to a completely different branch of mathematics, elliptical functions, which are like cubic functions on this side and squared functions on this side. And prove things about elliptic functions, and nobody understands elliptic functions all that well. It's a pre-calculus level phenomenon, but nobody's been able to solve it completely, okay? So at any level, there are questions you can ask that nobody can solve. Anyhow, digressing a little bit, but my point is, you come out of a pre-calculus course, if you're a top-notch student, you should be able to do this, okay? You should understand what the graph of this looks like. You should be able to do that much analysis without any calculus. Although then, in calculus, you learn a lot more about this thing, okay? And you can pull out all kinds of stops, and take derivatives and stuff like that, and see what happens to the derivatives. Okay. Well, end of the digression. But this gives you a pretty detailed picture of the way this thing behaves. And it's going to continue. So eventually it's going to just kind of become not a helix, but it's going to I'm not sure what you'd even call this, spiraling. Every revolution, if t goes on past 2 pi to many revolutions, every revolution is going to have a coil that's longer than the last one. Okay? Because, of course, z is increasing faster and faster. Well, it's actually increasing at a constant rate. So after a while, each turn of this spiral, this increasing spiral thing, is going to get longer at a constant rate. Each one's going to be about as much longer as the last one because of this asymptote. And that's worth thinking about, so I've just thrown that out. And of course we get to that by doing the calculus. All right, well, by contrast, the speed here is just the square root of 2. Okay? It stays on a circle, it stays above a circle, and it rises at a constant rate. Then your vector is always at 45 degrees to the xy plane and directed tangent to the circle. The xy components tangent to the circle, z component's always 1. So it's always the same speed around the circle, speed of 1, sine squared plus cosine squared, okay? And speed of 1 in the z direction.